All right, let's just jump right in. We are living in a world that is completely built on data. I mean, everything from our bank accounts to our video games, but what actually makes it all work? What keeps it from falling apart? Well, today, we're going to explore the fundamental, totally invisible principles that make our digital world reliable. And this quote just hits the nail on the head. We know data is everywhere, right? But it's so easy to forget that it can be flawed. Now, a good database design, it can't protect you from every single typo, but what it can do is protect against data that is logically impossible.
And this is the perfect example of what I'm talking about. This isn't just a simple mistake, it's a complete failure of integrity. The data is literally disagreeing with itself. I mean, think about it. A person can't have two birthdays. When you see something like this, it is a huge red flag that you have a bad database design, a problem that a process called normalization was built to solve.
So yeah, this exact kind of contradiction is the problem that early computer scientists were trying to fix. They realized they needed a structured, foolproof way to store information that would prevent these logical impossibilities from ever happening in the first place.
So the very first step to taming all this data chaos is, well, it's organization. A relational database structures information into these nice, neat tables, kind of like a spreadsheet you'd use. Each table holds a really specific type of information, and the columns define exactly what kind of data is allowed to go into them.
The best way to think about it is like a super-powered phone book. A phone book, it organizes names and numbers alphabetically. A relational database organizes information into tables. But here's the crucial difference: uniqueness. A database uses a totally unique identifier for every single row, which makes it impossible to have duplicate entries. And that unique identifier? It has a name. It's called the primary key. This is the absolute foundational rule. By telling the database that one column is the primary key, the system itself will stop you from creating two rows for the exact same thing. This makes it physically impossible for, say, a single person to have two different heights recorded at the same time.
Okay, so a primary key prevents the really basic contradictions. That's a great start. But to build truly robust systems, ones you can actually trust your money or your data with, we need a more advanced set of rules. And this set of rules is called normalization.
This quote gives us the perfect analogy for understanding normalization. Think of them as safety assessments. Imagine a bridge, right? Safety level 1 might mean it's safe for people to walk across. That's a basic guarantee. But if you want to drive a giant truck over it, you're going to need a much stricter assessment, like safety level 3. Normal forms for databases, they work the exact same way, giving you stronger and stronger safety guarantees for your data.
So, these are the first three safety levels. First normal form, or 1NF, handles the absolute basics, like just having a primary key. But second and third normal forms, they deal with much more subtle problems about how the data inside a table actually relates to that key. Let's see how this works in the real world.
To make this all feel a bit more concrete, we're going to look at a super practical example, designing a database for an online multiplayer game. Let's focus on a player's inventory.
All right, so here's our first attempt at an inventory table. At first glance, it seems logical. We've got the player, their rating, the item they have, and how many they have. But do you see the repetition? The player JDog21 has a rating of intermediate, and that fact is stored twice, once for his amulets and again for his swords. This kind of redundancy is a major red flag.
Now let's see why that repetition is so dangerous. Player Gila19 sells her only item, those 17 copper coins. To update the database, what do we have to do? We have to delete her row from this inventory table. It's the only way to show that she has 0 copper coins.
And here it is, the crucial problem. By deleting her inventory record, we have accidentally deleted her player rating. The database has completely forgotten that she's a beginner. This is what's known as a deletion anomaly. We lost important data we never, ever intended to lose.
So the fix for this is to get our data into second normal form. And the rule is actually pretty simple. Every single piece of information in the table has to depend on the entire primary key. A player's rating, it only depends on the player, right? Not on the combination of a player and an item. So that tells us we need to split our concepts into separate tables.
And look at this! This is the solution, and it's so much cleaner. We now have two tables. One is purely for inventory, and a separate one is just for players and their ratings. So now, if Gila19 sells all her items, we can delete her rows from the inventory table. But her record in the players table? It remains completely untouched. We haven't lost any data. Problem solved.
So we've solved the problem of data structure. Our tables are normalized, they're safe from those weird anomalies. But there's another completely different kind of problem. What happens when the operations we perform on that data are themselves unreliable?
Right, so now we're shifting gears to talk about the messiness of the real world. Unreliable networks, system errors, things that might cause the exact same command to be sent more than once.
I mean, imagine a high-stakes financial trading system. A request to buy some Apple stock is sent. The system executes the trade, but because of some random network glitch, the confirmation message back to the sender gets lost in cyberspace. The sender, thinking the trade failed, automatically tries again. Now what happens?
The system records the same trade twice. As you can see, it's a disaster. The data is now just plain wrong. It's showing double the purchase, all because of a simple network retry. Now, this isn't a problem with our data structure. This is a problem with our operations.
To solve this, we need a whole new kind of rule, a principle that protects us against these repeated operations. And this principle is called idempotency.
Okay, so an idempotent operation is one where doing it once is the exact same as doing it 5 times or 100 times. The system is designed to be smart enough to recognize that the second, third, and fourth requests are just duplicates of the first one, and it just ignores them. This ensures that the trade is recorded only once.
And this isn't just for Wall Street. Think about it. Anytime you click a buy button online, you are relying on idempotency to make sure you don't get charged multiple times if your internet hiccups. It is an absolutely critical concept for payment systems, for distributed databases, basically for any system where reliability is non-negotiable.
So at the end of the day, we've looked at 2 really powerful invisible rules that are the bedrock of our trust in digital systems. Normalization gives our data a safe and logical structure, and idempotency gives our operations the resilience they need to handle a messy, unreliable world.
And that really leaves us with this one last thought. It is not enough for our data to be well organized. It also has to be resilient against the chaos of the real world. True data integrity, the kind you can actually depend on, requires both perfect structure and resilient operations.